Hello, this is Ralph K. Gennaro with the Ancient and Medieval History Lecture for our online day, Friday, the 7th of October, 2022. As we're still in the middle of student presentations on creation myths, what we're going to do is focus now on our modern creation myth, which will be a topic that we will cover next week as we move from myth into prehistory. The modern creation myth is Big Bang physics and biological evolution. Now, you may say, but this is science. These aren't myths. Um, the thing about science these days, the thing you really need to understand, is that most people take the science on faith. How many people in the general population who have diplomas from high schools throughout the United States, or the Western world for that matter, really understand the scientific principles and the experimental data and the interpretations of that data that has come over the past century or so to shape and form these theories? Most don't. They assume that because a guy in a white coat and glasses who has a PhD or a doctorate after his name knows what he's talking about. And after all, our technology is so great, our theoretical science must also be so incredible that we can understand just everything with it. Well, when you believe in things you don't understand, as the musician Stevie Wonder once said, that's superstition. Most people in our society who believe absolutely and self-consciously and uncritically in Big Bang physics and biological evolution believe in it, they have faith in it, not from intellectual, logical persuasion, but because authoritative people at some point in their life told them that that's what one should believe. I will also fully disclose, for my part, I have no problem with being a believer in the Christian God and also believing that science has something interesting to tell us about how the world comes into being. I believe that Genesis 1 and 2 and the Bible in general tells the true story about why the universe is as it is, why people are as we are. That is what religion does. Religion does not deal in how as much as it deals in why. And had some time-traveling Whovian gone back into the ancient Near East and spoken to Abraham, Isaac, Jacob, and Moses about Big Bang physics and biological evolution, these largely illiterate, not the case with Moses, but the others, would not have understood. God, if one is a believer, spoke to the ancient Hebrews in a way that would be understood by the ancient Hebrews. Frankly, if one is humble enough and honest enough about our scientific understanding, it should be obvious that in a while, another century or two, assuming ongoing scientific progress, assuming that we do finally move from this cradle Earth into space, our scientific understanding centuries from now will look back on what we believe, what our society believes is scientific revelation, and laugh at it. Much the way that modern geologists laugh at the Atlantean notion of continents rising and falling. Science is not dogma. There's no such thing as settled science. Science is, in fact, the body of knowledge that we understand based in the Aristotelian philosophical principle of hypothesis, devising experimental models, going through the experiments, going where the data leads, and coming up with a provisional theory on the basis of that experimentation. Provisional until something better comes along, until a more full understanding comes along. So, I think, personally, you may disagree, that science may very well tell us things about how the universe operates, about what scale the universe is built on, and about how creation and life might happen, that in no way challenges or disproves my faith that the Lord God Almighty is behind it all. Again, this is a matter of opinion. But these are questions. Why do I believe in this? Why do I believe in that? That's important for people to understand. Because the most powerful force in a person's mind is an unreflected upon assumption. This is also called a prejudice, but it doesn't just mean racial prejudice or bigotry. A prejudice is a prejudgment that you, for whatever reason, have made that makes you decide that things are a certain way. And because you have decided beforehand that things are a certain way, whatever information comes your way through circumstances and situations is going to be filtered through that already pre-existent lens. You will not learn things outside of that unless you are willing to break the mold of that lens or question its fundamental assumptions. In other words, when you prejudge things, your mind is going to only recognize data that is within the frame of reference of your prejudgments, of your prejudices. Think about why you believe what you believe. That's one of the reasons that we're covering mythology. Because mythology is a collection of stories that people tell that try to explain how, but especially why, our lives are the way they are. Why human life and human civilization is temporary, mortal, flawed, fallible, filled with corruption and sin, but also the possibilities of glory and joy and salvation and wonder and all this other stuff. These myths try to explain all of that to some extent to certain people at a certain time. So, last thing on my own thoughts on this, well, for now. Do I believe in random evolution? No. Do I believe that the evolutionary process could very well be what brings complex life into being on this planet? Yes. But I don't think it's random. Whether it's some alien proto-molecule that has programmed into it progressive DNA changes that could produce from a virus-like earliest life form all the way up to what we are now and what we may become, that's possible. But I also think ultimately it's inspired by what I would call God, my own personal belief. For me, science and religion are different shoes. One for the right foot, one for the left foot, and I will get farther walking with both than I would with just hopping on one. In any case, what you believe and what I believe is less important than understanding what cultures of the past and present believe. So what I'm going to do now is go through my rendition of what I think is important about biological evolution. It starts out just over 15,000 million years ago, or 15 billion years ago, when the universe was composed of, well, it's not empty space. Empty space, as we understand it, is part of the fabric of our space-time. We have no bleeping clue what was before our universe. We have no bleeping idea what is or may be outside of our universe. It could be cotton candy for all we know. It could be a universe of nothing but shrimp for all we know. We don't know what was there before or what is now outside of our universe, of our frame of reference. Because we've never encountered it, we've never experienced it. So whatever was there is a matter for existential doubt. Then, bing, a geometrical point appears. Now, that geometrical point is chosen as the term because in geometry, a point is a location in a theoretical model of space-time that has no mass, that has no volume. It is a location without a real physical presence. In other words, it's the smallest thing we can possibly contemplate with our imaginations as human beings. It doesn't get smaller than a geometric point. But within that geometric point is theoretically the potentiality for everything that is, was, or ever shall be within our physical universe. And that bing is followed by boom! The Big Bang. It ain't called a Big Bang for nothing. That Big Bang is still going on. We are still in an ongoing explosion, a universe that is moving outward into what we don't know. It is an expanding universe, and we're somewhere in it. That means that as infinite without boundary as the universe seems to be, in fact, there is something outside of it into which we are expanding. Or at least, so logic would dictate. So if that is the case, what was before the universe? What is outside of the universe? We don't know. What we do know is we are in an expanding universe. We are still in the explosion that was originally begun by the so-called Big Bang. Now, in the earliest moments of the universe was an expanding sphere of white-hot, solid light, a state of matter and energy that's very difficult for us to imagine. Consider the space between subatomic particles. There's a huge inner space between subatomic particles, between the protons and neutrons that make up the nucleus of an atom and the electrons that make up the orbital cloud around it, and the space between atoms. Well, imagine solid light. Imagine a state of energy slash matter slash woo that is without space, without distance, utterly dense, utterly hot, utterly solid, a solid universe. And that solid universe is expanding. And then the first empty spot appears. And then other empty spots appear. This is a bit like the Chinese myth, where there's protoplasmic or protein chaotic soup, and then empty spots appear, and those empty spots begin to settle things out. Heavy things become solid, light things become airy, and yin-yang, so forth. In the case of our universe starts out as 100% solid light, and a state that we cannot possibly imagine. Infinite density, infinite mass, and nearly infinite weight. And then as open spots appear, the proportion of the universe that is solid goes down, and the proportion of the universe that is empty goes up, to a point now where dark matter notwithstanding, dark energy notwithstanding, most of our universe seems to be space between things rather than things. In other words, most of the universe is empty rather than solid, which it wasn't in the opening moments. So this is about 14.5 billion or 1,000 million years ago, about 15,000 million years ago, and the universe spreads out. Now, there are two motive forces at work in this early universe as things begin to develop. One is inertia, which is the principle Newton talked about. An object, once set in motion, tends to remain in motion unless something acts upon it. So, there is a tendency for the universe to fly apart. And that tendency, it can be called inertia, basic physical force, basic physical principle. By the way, there's a reason I don't teach science, as probably some of you more scientifically minded people will get, but I'm doing my best. The second is gravity. Gravity is the attractive force, because matter likes matter. Well, in reality, there is an attractive force. If we were floating in deep space, me and this pen, we would eventually, if we were close enough, tend to touch. We would drift into one another. Because, believe it or not, this pen has its own little gravity field. And I have my own gravity field. And these gravity fields tend to attract. Now, Einstein explained it this way. Imagine the fabric of space-time as a sheet stretched taut, completely tight. So you have this tight, horizontal, planar surface. It's a limited plane. It's a sheet, bed sheet, really tight. And you drop a bean on it. And you drop an egg on it. And you drop a baseball on it. And you drop a bowling ball on it. Boom! Each of those objects is going to dimple the sheet a little bit, cause the sheet to dimple down under the weight of the object. Now, the fabric of space-time is contorted by the existence of mass. The greater the mass, the greater the contortion. And that contortion, that dimple in the sheet, could be construed as the gravity well. So the Earth has a gravity well. And if we want to go into space, we have to gain escape velocity, which is to go fast enough, far enough, to get out of that gravity well. So the pen has a small dimple, just like the bean did. Our bodies have small dimples, just like the egg did. Objects like cars and trees have larger ones, like the baseball. And then there are worlds, moons and worlds and stars, and they're like the bowling ball or bigger things. They'll really rip through that. And in fact, the notion of something ripping through the fabric of space-time is what a hypermass is all about. That is a black hole, which is an object with approaching infinite mass. And so instead of the dimple in space-time being really deep, it's a hole in space-time into which we don't know where it goes. We know that light itself can't escape from a hypermass or a black hole. Light itself, as light as it may seem, is too heavy to escape, and it gets sucked in. So around every black hole is what is called an event horizon, the point at which light itself is sucked in. Any matter that would be sucked in would be spaghettified, that is, stretched out of all and distorted out of all recognition, which would be painful. And time itself distorts because space and time are, according to Einstein anyway, relatively the same thing. So, matter and energy, inertia and mass, or inertia and gravity, form these proteal forces. So when a moon orbits a planet, for example, the moon is flying off into space, that's inertia, but it's also being sucked into the center of the planet, that's gravity. And a stable orbit is a balance between these two forces. The gravitic force balances out the inertial force, and instead of flying into space or flying into the center of the planet, the moon describes an elliptical course around whatever body it's orbiting. Okay. So that's somewhere around 14.5, 15,000 million years ago. Then primal dust begins to attract, begins to collect, begins to gather, and that attracts more dust, a bigger gravity well, more of this primal, chaotic sand gets into everything. And it gets more massive, and there's more of it, and the gravity well increases, and there's more mass, and there's more of it, and the gravity well increases until suddenly, finally, the pressure increases, and with the pressure, the heat increases, and with the heat and pressure increasing, boom! The first star is born, about 13 billion years ago, maybe 14. 13,000, 14,000 million years ago. Gravity ignites the dust. And then other stars begin to form as the dust begins to settle out, and the heavier dust creates centers of gravity so strong that you end up with heat and friction and pressure and explosions, and the atomic furnaces that are stars ignite. Now, stars gather around them an accretion disk of waste matter, or matter just from the universe of all kinds, various elements, water, metal, rock. And these tend to form lenticular shapes, that is, the shape of a lens. It's sort of a disc shape, with the center of the disc being the star. Now, there are some star systems that don't follow this pattern, but in general terms, this lens shape regarding gravity is seen again and again. And it has to do with the star's gravity drawing things to it, the inertia of the existent movement of the planets creating a gyric effect, a spinning effect. And so you have the planets, or the rings around the stars, orbiting in a certain plane, because these objects not only are acted upon by the sun, they're acted upon by one another, which tends to move them and shift them into a disk, what we in the solar system call the plane of the ecliptic. So planets are going to form around stars out of this disk, and we'll talk more about that later. The stars themselves, though, are organizing into large conglomerations, and these conglomerations are called galaxies. Now, our Milky Way galaxy forms about 10 billion or 1,000 million years ago. It's an island universe in the shape of a great lens. The Milky Way galaxy, at the heart of it, seems to be a supermassive hypermass, or a gigantor black hole that is slurping up the stars of our galaxy. Our galaxy exists in a whirlpool type effect, and that whirlpool type effect is in the form of several galactic arms, the Orion arm, the Perseus arm, the Sagittarius arm, and so forth. And we're about two-thirds of the way out from the galactic shapely center, basically an offshoot of the Orion spiral arm of the galaxy. What's going to happen to our galaxy? Well, the force of inertia is keeping the stars in the lens spinning. In other words, they're trying to shoot out, but they're being drawn towards the center. Ultimately, if our galaxy were left alone, either entropy would take over, and the black hole would lose its grip, and the various stars would fly off into intergalactic space, or the black hole would win and slurp up everything. But long before that happens, the Andromeda galaxy, which is about twice as large as ours, and at its center is a supermassive hypermass, or a superhumongo black hole at the center, and our galaxy are going to collide. And that means that when that happens, which is a long time from now by human standards, the galactic centers will whirl around one another. Planets will be ripped out of their orbits around stars. Star systems will fall apart. There'll be collisions, but mostly it'll be gravity reordering the delicate balances that have existed heretofore in both galaxies. And ultimately, both galactic centers will orbit one another until Andromeda slurps up the center of the Milky Way galaxy, and a new galaxy is formed out of whatever the heck is left after both galaxies collide. So the universe, as I tried indicating on day one, is really big. And these two massive island universes are specks of sand in the open sky. The universe has many galaxies, many galactic clusters, and it's just unimaginably big. And it, according to physics, is continuing to get bigger. About 6 billion or 1,000 million years ago, between 5 and 6 billion or 1,000 million years ago, a nearby star goes nova. And what that means is it's dying. And some stars with insufficient fuel just wither. They die with a whimper. But some stars that have a sufficient backlog of atomic fuel basically say, better to burn out than fade away. And they go nova or supernova. They basically do what an incandescent light bulb does near the time of its death. They end up consuming all of their fuel or most of their fuel in an orgy of excess that lasts a few hundred or maybe thousand years. And they put out shock waves of gravity forces and great amounts of radiation and light. When it happens in our solar system, the surface of the sun will be somewhere between the orbits of Mars and Jupiter. Maybe conditions like us, like we're used to on the Earth, might exist briefly in one of the moons of Neptune. Who knows? What we know is sooner or later it'll probably happen to our sun. Probably not anytime very soon by human reckoning, but at some point. Jupiter is an example of a star that fails to ignite because it doesn't have quite enough atomic fuel to make that happen. So it's a brown dwarf. Had Jupiter actually sufficient atomic fuel, it would have ignited and we'd have a binary star system. We'd have Sol, our big star, and Jupiter, our little star. Anyway, so about 5.5 billion years ago, there's this nearby star that goes nova or supernova, and it sends out a gravitic shock wave. Now, there's a local dust cloud, and in that local dust cloud is all the potentiality of everything in our solar system. And as it starts getting impacted by the gravitic shock waves, densities begin to form that begin to organize the dust cloud into clumps. And there's a really big clump where there's heat and there's pressure, and there's heat and there's pressure, and boom! The heat and pressure become Sol, our star. And at first, our star is surrounded by this cloud of rocks and debris. But after a while, the rocks and debris settle into a lens shape. Like the planet Saturn has rings around it, our sun would have basically rings of rocks like a bunch of super asteroid belts. This happens about just over 5,000 million years ago, or 5 billion years ago. Now, these rings around the sun begin to themselves collect and clump and swirl and ultimately produce 9 planets and a bunch of other things. The inner rocky planets, there's Mercury, which forms as a planet, and it's tidally locked, so it has one face always aimed at the sun and one face always shaded from the sun. And it's close to the sun, and it has a very short year being the amount of time it takes to go around the sun. And you've got Venus, which is approximately like the Earth, except that Venus is like hell, at least what people picture as hell. Venus has this super heavy, thick atmosphere that collects heat and radiation and pressure. So on the surface of Venus, a human being would be pulpified. Their flesh would become like a ball, and their bones would be crushed. That's after the flesh left the bones. And we'd also probably just scorch and burn and roast and die, because the surface of Venus has an air pressure that's so heavy, nothing that we are as living things could survive that. The Russians have sent a variety of Venera probes to Venus, and they all last, the best of them last a few hours, because the conditions on the surface of Venus are just so unpleasant. Mars develops. It probably at one point has a better magnetic field than it does, a thicker atmosphere, maybe even surface water. But things happen to Mars. And Mars today, one of the differences between Mars and us is its atmosphere is much thinner, and it does not have a planetary magnetic field. We have a North Pole and we have a South Pole, and that gives our planet a magnetic field, which is like a deflector shield against many forms of cosmic radiation, allowing life to form on Earth. Otherwise, the sun is basically a giant scorch ray. So Mars, not life. Now, at one point, there was a fifth planet between Mars and Jupiter. But that fifth planet's orbit strayed too close to Jupiter, and it basically got ripped apart and became Ceres and the rest of the asteroid belt, a bunch of rocks that orbit the sun like a ring. Then you've got beyond the asteroid belt and beyond the inner rocky planets, Mercury, Venus, Earth, and Mars. We'll talk about Earth in a bit. You've got the gas giants. You've got Jupiter, which is, again, a brown dwarf, a failed star with a bunch of rings and a bunch of moons, including Io, which is a volcanic moon, the only moon that we know of that has volcanoes like we do, and Europa. Europa is a moon surrounded by a frozen bubble. And within that frozen bubble, many believe that there is a liquid water ocean. So if there is anywhere in the solar system that has life like the Earth, it might be under the icy roof of Europa. You might have an actual oceanic life food chain, a set of food chains, environment, biome between the frozen surface of the frozen atmosphere of Europa and the rocky planetoid that it is. There is Saturn with its grand rings, first spotted by Galileo Galilei in the 1600s, and its moons. There is Uranus, which is weird because, unlike all the other planets, say my head is the sun, the planets tend to rotate like this, so you have day and night in most cases. Uranus rotates like this, so it's like rolling along, like a ball rolling on a pool table, but in an orbit. And Uranus has a moon called Miranda. And Miranda existed floating along, and then boom! And it was almost exploded by some kind of cosmic collision with something really big or really fast, or both. And so the surface of Miranda is normal moon, normal moon, normal moon, and then scar tissue over close to half of it. And that scar tissue looks like scar tissue. It's what's left over when a moon goes and reforms over a vast part of its surface. And then there's Neptune, which also has rings. It has a storm like Jupiter has. Jupiter has a storm the size of, is it the size of Texas or the size of the Earth? I think it's the size of the Earth. And this storm has been going on since Galileo's time for close to 500 years. This big tornadic gyre of a storm. Well, Neptune has a much smaller version of that. And then beyond Neptune is the Kuiper Belt, including planet Pluto and its moon Charon. And there are a number of other planetesimals and dwarf planets in the Kuiper Belt, which is around the gas giants. And beyond the Kuiper Belt is the Oort cloud. And near the edge of the Kuiper Belt in the Oort cloud is planet Sedna, which is another planet out beyond Pluto that has a very, very, very distant, very erratic orbit. And so beyond the Kuiper Belt, which are these rocky objects, there's the Oort cloud. And unlike everything else that sort of works in this lens area of gravity at the plane of the ecliptic, the Oort cloud is sort of a spherical cloud of comets. And these comets occasionally come in and get baked by the sun and then go out again. Halley's Comet, or Halley's Comet as it's properly called, comes in every 70 or 80 years. It comes in, it's charted by people, people go, oh, it's a sign of doom, and then it leaves and goes back again. But other comets come and go much more randomly. And comets are basically like giant dirty snowballs, rocky snowballs with lots of rocks in them. And when they get close to the sun pulls away a lot of the water ice, and the comet looks like it has a tail. But the comet tail is not following its movement. The comet tail is always aimed at the sun, or in relation to the solar winds. So this is about 5 billion years ago. The solar system forms, and the early Earth forms too. And the early Earth forms with a variety of spheres. So at the heart of the Earth is the nickel-iron core. There are two layers of that, the deep core and the outer core. And basically what this is solid nickel-iron, heavy metal ball that counter-rotates to the surface of the Earth. So on the surface of the Earth, there is the sun rising in the east and setting in the west. If you were standing on the core of the Earth, on the surface of the core of the Earth, the sun would rise in the west and set in the east. And this counter-rotating core is one of the reasons why we have a magnetic field, a planetary magnetic field, which is one thing that protects us from cosmic radiation. So there is the core of the planet. Above the nickel iron core of the planet is the mantle. Now, the mantle is composed of what is a lot like soft serve ice cream. But what soft serve ice cream made of liquid and semi-liquidic metal and rock. You think lava from a volcano is hot, not compared to various parts of the mantle. And the vast majority of the sphere that is the Earth is this, the volume is this mantle. This sort of soft serve ice cream of liquid metal and rock. So you've got the counter-rotating core, rotating as opposed to the surface of the Earth. You've got which is solid. You've got the mantle, which is sort of gooey. And then, since space, except in the direct sunlight rays of the sun, is cold, the outer edge cools. It's a bit like chocolate shell in a soft serve ice cream cone. So if you've ever gotten soft serve ice cream and had it dipped in chocolate shell, what that does is you've got this sort of gooey stuff that's like the mantle, and you dip it in chocolate shell, and then you've got this solid outer area. Well, the coolness of space, the relative coolness of space, solidifies the surface of the Earth. And in being solidified on the printer, it creates an outer crust. And that's what we live on. But if you've ever had chocolate shell, you know that after a few minutes it cracks and there's stuff that oozes out from the ice cream, the chocolate or the vanilla or whatever your ice cream is. So this is the crust, and the crust is made of several plates. And each of these plates moves against one another, and there are little explosions in it. And these explosions, these little leaks, we call them volcanoes or volcanic rifts. So the volcanoes are emitting magma onto the surface, which we, when they're on the surface, call lava. So you've got the cores, the outer and inner core. You've got the mantle, which is the majority of the volume of the Earth. You've got the solid crust of the Earth, which is about 100 miles thick, which is where we keep all of our stuff. And around that, you've got sort of a gaseous layer of dust and mist, which is working through various stages of cooling. And as this is happening in the proto-Earth, minding its own business, orbiting the sun, I got the tone wrong. Hey, what's that? What happens is another planet whams into the Earth. And the Earth explodes, but it doesn't completely dissipate. It doesn't become another asteroid belt like the planet between Mars and Jupiter used to be. No, what happens is it goes, and then it reforms. And an entirely new Earth is formed, which is a hybrid, a Reese's peanut butter cup, a alloy of both the old Earth, the original Earth, and this new planet which came in and joined with us. Now, the new Earth has so much debris that was shot into orbit, which is a mixture of both the original Earth and the new planet that came in, is now going to be orbited by a single large moon. And that moon is going to be important because the moon runs interference. It's like a shield for the planet. You see all of those craters on the moon? All of those craters on the moon could have been impacts with the Earth. But instead, what happens is that as the Earth moves through a rocky, dangerous solar system filled with flying rocks and comets and things, what happens is the moon's gravity will draw many of the things that would otherwise hit the Earth into its own orbit and at least causes them to deflect and not hit us, or maybe hits the moon instead. So you have the proto-Earth, which is a combination of the original Earth and the new planet, which is reforming. And there's the crust, and there's the mantle, and there's the core, and there's the mantle. Stop. And there's the crust. And you're making noise. And the crust is where we keep all of our stuff. But then, as the crust cools, What happens when vapid air that's filled with vapor, cools? Well, what happens is the water is drawn out of the air and falls as rain. So rain, thousands of years of rain happens in the early earth. And that thousands of years of rain causes the seabeds to fill. But what happens when you wet ferrous metal, that is metal composed largely of iron? What happens to the iron? What happens is it rusts. So the early oceans of the world are rusty. And this lasts, again, several thousand years, rusted oceans. So around the crust is, or the lithosphere, as it's fancily called, is the hydrosphere, which is the thin, oily sheen of water over the crust of the Earth, covering, what is it, 3/4 of the Earth? Most of the Earth, 3/4, 4/5, something like that. The vast majority of the Earth is covered by the hydrosphere. And then beyond the hydrosphere are the various thicknesses of atmosphere, which is the gaseous sea of air that we all exist in. At the bottom of, we crawl along the bottom of the sea of air. And the atmosphere gets thinner and thinner, and there are various chemical layers like the ozone layer. And then beyond the atmosphere is what is created by the counter-rotating core as opposed to the surface, and that is the magnetosphere. And the magnetosphere is an electromagnetic shield that is described by the North Pole magnetic pole and the South magnetic pole, protecting the Earth from cosmic radiation. So what we have done on this Friday, ancient and medieval students, is we have covered the history of the universe from before the Big Bang all the way through the shaping and creation of the various levels of the sphere of the Earth. Now, your job is to comment upon this. In the area below this video, you are to write a paragraph in response that is thoughtful about something that I mentioned, where you explore an idea, where you consider its implications, where you consider its meanings. Gravity and inertia. Gravity igniting the dust, lenticular galaxies forming, black holes, all of this stuff, and the Earth itself forming its various discrete layers. So comment on it. Be sure that your comments are done by the time deadline that I told you, and have a great weekend.